We'll conclude this module with a discussion of two different models. We'll look at models of linear growth and then move on to exponential growth. Linear growth can be considered sort of the more basic of them. Exponential growth is somewhat more complicated, but both are really foundational in the subject of mathematical modeling, which is you have some sort of real-world scenario and you'd like to write a mathematical function that governs the relationship. So let's start with linear growth. Right, so just to summarize kind of the key differences first, we can have complicated models, but two good starting points would be linear and exponential models. And typically what one does is one builds on these. Now the salient points for each of them is, for linear models, the rate of change is constant. So we'll talk about functions that are modeled as lines that have constant slope. For the exponential models, the rate of doubling is constant. So instead of being constant slope, we know that after some fixed amount of time, things double. Or maybe not double, but increase by some known geometric factor. So what do we mean by linear? Well, just to recall, we mean things like first-order polynomials, like ax plus b. And then we look at functions like that, f of x equals ax plus b. And our goal here is to say, given y, can we compute x? Given x, can we compute y? Is the relationship governing x and y linear or not? Typically, in a word problem, you would know that the thing is a linear system or a linear equation if the rate of change is constant, that as I create or produce more of something, the cost that I pay is just constant in the number of things that I produce. So here's a kind of standard example. What is a widget? I mean, no one really knows. Someone knows. But this is just like a kind of an economics term that's often used for, you're talking about some sort of business or economic system, but you don't really care what it is that you're creating. It could be toothbrushes, it could be cars, it could be anything. So they use this funny term widget just to de-emphasize whatever it is you're making. But the bottom line is, we're going to make widgets, and how much does it cost to make a widget? It costs $20 per widget. But no matter how many widgets you make, you also have to pay a startup cost of $1,000. So there's sort of like a fixed price at the beginning, and then for every new widget, you pay $20 more. So how do we model this? Well, I claim that this is a linear model. How do I know that? Well, for each widget that I create, I just pay a fixed rate of $20 per widget. There's no sort of more complicated relationship than that. So this indicates that we have a constant cost slope, which indicates a linear model. So I'll say that the cost function, C of W, so this should be thought of as like cost per widget, depends on two things. It's $20 per widget, but then I also have a fixed startup cost. I have an amount that I'm going to pay no matter what to make widgets, and that's $1,000. So plus $1,000 for the startup cost. Right, so notice C of W is a line of slope 20. So it is indeed a linear model, and the slope of the line corresponds to the rate of change in the cost of manufacturing per widget.